class is called uniform cost search. Till now, whatever searching algorithm we have seen, all are having first initial state, which is also called a start state. It will have what are the action that it will can take, right? It will have what we mean by goal state, right? It will calculate the state transition with the transition diagram, transition model. And it will find out the path cost at last. But this uniform cost search and whatever searching algorithm we have seen breadth first search, we have seen depth first search, we have seen iterative depth first search, we have seen limit depth first search, and we have seen bidirectional search. So in all these searching algorithm, we are calculating the path cost at very last. Okay, once we'll got the solution, we'll find out the path cost. But this path cost will be taken into consider from the first step in the uniform cost search. That is the difference between the other searching algorithm and this uniform cost search algorithm. That's why uniform cost search algorithm we are saying at very last. So what it is saying that when all step costs are equal, the breadth first search is optimal solution. It always expand the shallowest unexpanded node. It is saying that breadth first search, this BFS, will giving you a great solution, a good solution, if all the step costs are same. All the step costs are same means from reaching to starting state from A and B, you have the same cost. Let's say 1 and 1. From reaching from A to C and D are also the same. So what happened into this uniform cost search? It says that the breadth first searching algorithm will give you a optimal solution if all the path cost will be the same. But in real world, this is not the scenario. Okay. So what is the scenario? Scenario is from reaching from one state to another state, your path will be different, maybe different. It is not the same. If it is not the same, then whatever path you have taken, how you will consider that it is an optimal path, right? So to take that question in mind, the scientist has come up with an idea of uniform cost search. By a simple expansion, we can find out the algorithm that is optimal with any step cost function. Instead of expanding the shallowest node, uniform cost search expand the node n with the lowest path cost. So it is not talking about the shallowest. Shallowest means how quickly or how without going to the deep, if we have the solution at very particular state or very particular level, so we are getting it. That is called shallow. Shallow means it is there in near to your less level. So if your solution is in less level, definitely the breadth first search is the best solution for that. But the thing is that all the time the shallowest may not be the solution. So let me take you an example so that you can understand what I'm saying. I want to say that if you are starting from, let's say, the starting state, you are going to some intermediate state and you're reaching here. Let's say I have some costs. This is 1, this is, let's say, 19, and this is, let's say, 3, this is, let's say, 2. Let's say you have goal state. This is your goal state. And let's say this is your goal state. Now, what happened when we take the breadth first search? Breadth first search will expand in one depth. So first it will expand the 0 depth. So in the 0 depth, do you have goal? No. In depth 1, do you have goal? Yes. So you have the goal, then it will come out. This algorithm will come out. What is the path cost? The path cost is 19. Path cost is 19 in the solution of breadth first search. Now this path cost is an optimal path cost, or this solution is an optimal solution? No. Optimal solution is this with the path cost of 3. As you can see, this is the goal. This is the goal, okay, but this is also a goal. It means that from here to the railway station, we have different paths. Which path will be the optimal path? How you'll get to know? When you explore all the path, right? If you know only one path, then it will be your optimal path. But you know that there are different paths to go from here to railway station, and you'll have some cheapest solution, some optimal solution. To take that particular thing in mind, the uniform cost search has been created. And it says that instead of going to the, instead of finding the goal at once, will not say that this is the goal. We'll find out other goals with the less path cost. So the path cost is the criteria for taking all the decision. So the uniform cost search expand the node N with the lowest path cost, which is denoted as GN. GN is the path cost of that particular node N. This is done by shorting the frontier as the priority queue order of G. The algorithm is shown in the figure. Now, the front, as I told you in the last class, there are two types of data structure. One is called explode, another is called frontier. Explode are the set of nodes which are already been explored, or already been, we have find out the children of that particular node. And frontier node, or the list of the frontier, are nothing but the node that yet to be expand, right? So we have these two type of data structure. So based on these two type of data structure, we'll search that which particular node will be expand next. So which particular node will be expand next? To take the decision, we have different searching algorithm. In the breadth first search, we have seen a different way of finding out that which particular frontier node will choose first. In breadth first search, we have seen that which particular frontier node we have to choose first. So for that, here also we have the criteria. The criteria is your frontier queue or your frontier data structure should be a priority queue, and it would be ordered, it will be sorted based on the path cost. So whose path cost is less will explore that one. Whose path cost is less will explore that one. That is the criteria of uniform cost search. Okay. So let's see one example and try to understand that what this algorithm is saying. Okay. So first see the algorithm, and then we'll see that how we'll take one example of out of that. Okay. So first we'll see the algorithm. So this is my algorithm, right? Let's see the algorithm, what it is saying. It is saying that it is a uniform cost search. It will take the problem. Problem means all the 5 components which we have seen in the goal formulation and the problem formulation. And it will return the solution if the solution exists into the state space diagram, or it will return the failure if it is not there. The first variable that we'll take is a node. Node is nothing but your initial node. Initial node means from where your agent is right now. What is the initial state of your agent? So that state is nothing but your initial node. Then there is a list of frontier nodes. So frontier node are nothing but the nodes which yet to be explored. And here it is saying that it should be your priority queue, and that priority should be ordered with the path cost, with the node as the only element. So initially that node, the initial node, will be your only element there. Explode is the set of node which is already been explored, and initially it will be empty because we haven't explored any node. So initially it will be empty. Now we'll apply the loop. In the loop, the first condition is the frontier list is empty, means no nodes are left to explore. If no node are left to explore and we didn't find the solution, then there is a failure. Else what we do is we'll pop the frontier node, right? Pop means we'll delete the frontier node, one of the frontier node. And how we'll choose? We'll choose the lowest cost node in frontier node. So we'll find out the lowest path cost, and that lowest path cost node will just delete from the frontier list. If problem dot goal test node dot state, then return solution node. If that particular frontier node is the goal node, then we'll send the solution. Whatever we have just deleted is deleted from the frontier node. Is that particular node is my goal node? Is my goal node? If it is a goal node, then I'll send that particular node as a solution. Otherwise, what we'll do is I'll add that particular node into the explode list because I have been already explored. And in the exploration process, what I'll do is whatever action I have, I apply in that state one by one. And if I am getting into the next state, I'll take that particular next state as a child state. And this child state is if it is not there in the explore list, or if it is not there in the frontier list, so I'll add that particular child into the frontier list. Else if what I'll do is that particular child that I have just explored is in the frontier list, it is already in the frontier list, then I'll see whether the cost is the high cost or not. The previously frontier node has the cost, path cost is high or not. If it is high, then I'll replace the whatever explode node I have just explored, I'll replace with the frontier node as a child because I find out the less path cost. So in that way, it will go on and on. This particular process will go on and on till we'll get the solution or till we'll get the failure. So this is the point where my algorithm will go out from the loop. Okay. So this is a algorithm. Let's try to solve a problem by using this particular algorithm. You all have learned about the Dijkstra shortest path algorithm in the algorithm subject. Okay. And this uniform cost search is the modification of Dijkstra algorithm. Okay, we'll see about that into next slide, after few next slide. So this is my problem. Okay, and this is my algorithm. So I am putting the problem, I am putting the algorithm side by side so that I can refer it. And then I'll create the solution for it. Okay. Now let's see. So what we have right now, we have this initial state. This is starting state, and this is the goal state. In between, we have different states, and in the edge, whatever number it is written, this number is nothing but the cost, the path cost. Okay, so what is the thing? Our thing is we have to start from the starting state, and according to the algorithm, we have to reach the goal. We have to find out the goal. Okay, so let's start from the beginning. So what two thing that we have to see is, here we have three three different variables. One is the node, another is the frontier, and next one is explode. Node is your initial node is your node. So what is my initial node? Initial node is S. So here I have S at very beginning. Okay, what is in the frontier? So frontier is nothing but the Q. It is look like a Q. So I am making this like a Q, and initially it has the node as the only element. So what is a node? Node is S. So S will be the only element here. Now there is an explode list. So I'm making the explode list also. This particular explode list, initially it is empty. Nothing is there. Okay. Now we'll start the loop. It says that frontier is empty or not. If it is empty, then we'll return the failure. Frontier is empty? No. In the frontier, there is one node. So this condition is not satisfied. So we'll go to the next one. So what we'll do is we'll pop the frontier. So whatever is in the very, because it is a priority queue and we have to make order list. So what is in the front of that particular queue? So in queue, if you'll go to the post office for posting your speed post, so you'll make the queue, right? So queue means whoever is coming first will be given the first chance for posting there later. Now the queue will go reduced and reduced once the other person will be getting the chance for their speed post, right? So the same thing will happen into the queue. So you will go and get the ticket in your, let's say, if you're going to the theater, so you'll go and make a queue and take the ticket and you'll go out. So who will get the first chance? Who has in the front of the queue? So I'll make the ordered path all the time, or I'll choose those node who has the lowest cost, lowest cost, right? So because S is the initial state, it has the cost 0. So definitely this is the lowest, as well as this is the only frontier node. So we'll pop it. So we'll just delete it. So we'll pop it and then we'll test the goal node. What is my goal node? Goal node is G. So I have to test it. What we have to test it? That S is equal to G or not. S is equal to G? No, it is not. Then we'll go to the else part. It says that add node state to explode. This particular node state to explode. So S will put it into the explode list. Getting it? So we have removed S from the frontier. We have added into the explode. Now again, loop is there. This loop will find out all the actions, perform all the action and find out all the state, all the child of that particular node. So we'll find out the child. So initially we are in state S. Now what we have to do is we have to explore all the child. So what are the child we have? A is one child, B is another child, and C is another child. So we have three children of S is having the cost 1, having the cost 5, and having the cost 15, right? Now we find out the child. So first child is A. Who is the child? Right now the child is A. A state is not in the explode or frontier. A is there in the frontier? No. A is there in the explode? No. Then what we have to do? We have to insert it into the frontier. So we'll insert it into the frontier. So A will be inserted into the frontier. Okay. If the child state is already in the frontier, then we have to see whether it is a higher path or not. Because A is not in the frontier previously, so will not go in that particular line, because this is not satisfied, because A is not in the frontier previously. This line satisfies because A is not in the explode, not in the frontier. So I am putting into the frontier. Now what is the next? Next child is B, because it is a loop. So we'll go on and on and on. So the next child is B. B is there in the frontier or explode? No. So what we do is we put into the frontier list. Next child is C. C is there in the frontier or explode? No, is not there in both. So C will be added into the frontier, right? Right. And it says that frontier list should be the priority queue ordered by the path cost. So what is the path cost? We haven't calculated the path cost. Let's calculate the path cost. So what is the path cost? I am calculating the path cost from S to A. How much cost? Cost is 1. From S to B, what is the cost? Is 5. From A to C, what is the cost? Is 15. Right? So this is my path cost. So based on the path cost, we have to do the order. So A is the least cost, so it will come first. A is coming first. Then B is after that, because it is a 5 cost. So B is coming after that. And C is the 15, is the maximum path cost. So it is coming at very last. So it is already in order. We doesn't have to reorder it. Now, what is the next step? We are out of the loop. Again, we'll see. Frontier is empty. Frontier is empty? No. Frontier has A, B, and C node. So what we do is we pop the frontier. So which particular node we have to pop? Because we have to pop what? A. A we have to pop. Why we have to pop A? Because A is in the first place right now, right? It is because we have make a priority queue. So based on the priority queue, it is the least cost. So what is the least cost path? A is the least cost path. So we have to explore A. So A will be removed from the frontier and check with the goal So let's check with the goal. A is equal to G. This is the next step to check the goal. This is the next step. This one to check the goal. It is in the goal state? No, it is not the goal. Then what we have to do? Then add the node into the explode list. We have added into the explode list. And then we have to find out all the action to explore the child. So what is A child? What is the child of A? Child of A is S and child of A is G. See, S has already been in the explode list, right? We doesn't have to go again. So we'll go to those node which is not explored. So it is G. What is the cost here? Cost here is 10. Let's find out the path cost. What is the path cost? This is 1 plus 10, it will be 11. 11 is my path cost. What is it? 11 is my path cost. Now what is my child right now? What is my child? Child is G. So G is my child. Now G is there in the frontier list or in the explode list? No, neither is in the frontier list nor in the explode list. So we have to put into the explode list. Is it there? If child is not in the explore list, frontier list, then add into the frontier list. So we have added into the frontier list. And then we'll reorder the frontier list based on the priority queue. So what is the cost of B? Cost of B is 5, which is less. Cost of C is 15. And cost of G is 11. So whose cost is less? So G cost is less. So G will come here, right? So what we do? We'll update our priority queue. So it will be B, and after that G will come, and after that C will come. Now, is frontier node is empty? No, it is not empty. Then we'll have to pop the frontier node. So which we have to pop? Definitely B has the least cost. See, G, B, and C are the frontier node, which yet to be explored. So if G, B, and C are yet to be explored, which will explore? Whether it's to explore B or G or C, definitely will explore B because it has the least cost, which is 5. 5 is less than 11 and 12, 15. So B will be popped up. And after popping, we have to see whether it is a goal node or not. So we have to check whether the B is goal node or not. It is not G. So if it is not G, then what we have to do is we have to put it in the explore list. Already put it into the explore list. Now, what we have to do, we have to find out all the states, all the child from that particular state. So from B, where we can go? S is already been explored, will not explore it. Then we'll explore G. The node which is already been explored, we doesn't have to explore. But the node which is not explored, we can explore. So because G is not explored, we can explore it G. Now we'll find out the cost of that particular node. 5 plus this one is 5. 5 plus 5 is will be 10. This is my path cost. It is taking 5. So 5 plus 5. So 5 is there. 5 plus 5 will be 10. So I am getting 10. This is my child. So I am getting G. But this G has less cost than this G because this G has 11. So we'll apply this particular condition. This condition says that the child state in the frontier with the higher path cost. Do we have higher path cost here? Yes. So we'll replace the frontier with the child. So this child will be replaced here. So this is G, this is the G. But this G has the cost what? 11, and this G has the cost what? 10. So this G will be replaced. So this G with the cost 10 will be replaced. Now, next is again, if the frontier is empty, do our frontier is empty? No, there are G and C. Then we'll pop. So which one will be popped? So here, this G is yet to be explored and this C is yet to be explored. Who is having the least cost? So definitely 10 and 15, 10 is having the less cost. So just G will be removed. After G removing, what we do is we'll do the goal test. Whether the G is equal to G or not. Yes, G is equal to G. Then what we do? Then we'll make it as a solution. We'll make it as a solution, as you can see here. So the G is my goal node. I find it out, and this is my solution. So if this is the solution, then what is the path? The path is from S we can go B, from B we can go G. This is my optimal path. See, this uniform cost search will give you optimal path. How it is giving you optimal path or optimal solution? S has already been explored goal node, but the cost is 11. So this algorithm will give you the goal with less path cost. Okay. So we'll apply the uniform cost search in the state space diagram, and we'll find out the solution, and that solution is the optimal solution. So what is your path? Path should be from S, we can go B, from B, we can go G. And what is the path cost? The path cost is minimum, it is 10. So this is your example related to the uniform cost search algorithm. In addition to the ordering of the queue by path cost, there are two other significant difference from breadth first search. So what are the difference between the uniform cost search and the breadth first search? The first is that the goal test is applied to the node when it is selected for expansion rather than it is first generated. So goal test will be taken care here. See, when the G is generated, we haven't compared with the goal, right? When it is removed from the frontier, then only we have compared with the goal. So in that way, we are getting the optimal solution. The second difference is that the test is added in the case the better path is found to node currently in the frontier. So we find the better path because of the frontier list. Because frontier list is in the order, is in the shorted form based on the path cost. So we'll find out the better solution. Now we'll see this example. This is another example and we'll find out the solution for that. This is the problem that we have already seen, and that problem is the Romania city problem. In the Romania city, these are different, Romania, we have different cities, and our objective is to go from one city to another city. Okay. So our problem is to, if we are in one city, let's say we are in Arad, so we reach to the Bucharest. So what are the different paths that we have to take so that we'll get the optimal solution? So the one part, small part, has been taken here as a problem, and we have to find out the correct solution using the uniform cost search, and we'll apply the depth first search also. So we'll apply two searching algorithm here to get the solution. Okay. So we'll make it quickly. So this is my problem. Okay. So I'll not write the whole city name. I'll write Suboi as S, Figueres as F, Rumiki Velika as RV, Pitesti as P, and Bucharest as B. Okay. So I'll find out the solution with one by one. So first we'll apply the, okay, it is making a difference with breadth first search. So let's say we'll apply the breadth first search first. Now what is breadth first search? Breadth first search will find out the solution if the solution is in shallow node or in the shallow level. So we'll apply breadth first search. The initial state is Subui and the goal is Bucharest. Okay. And intermediately we have some state, and these are the path cost. So in the breadth first search, we are not bothering about the path cost. We are calculating the path cost at very last. So it will not make any changes in the finding out the solution. So we are starting with Subui. This is in 0th level. In the breadth first search, we'll explore in one depth at a time. So from Subei, what we can explore? We can explore Rimnikiu Velika. So we'll write RV. Okay. And we'll test. So what happened in the breadth first search? We have two lists, right? Just like the uniform cost search. We have the frontier and we have explore. So in the frontier, we have okay. So in a frontier, I'll put those nodes which are at very start. So start, I have the Subui, right? Now we'll take the Subui from the frontier and we'll compare with the goal. Is it so? We'll not do it here. We'll just do it at very first. At very first when we have explored. So S is my goal node. No, S is not a goal node. So we'll remove S from the frontier and we'll put it into the explored list. So we have removed S from the frontier. We have put it into the explored list. And after doing that, we'll find out all the nodes from the Subui. So we have RV. So RV, once we find out RV, we'll compare RV with the goal node. Is a goal node? No, it is not a goal node. Then we'll explore another child, which is Fagaras. Fagaras is a goal node? No, it is not a goal node. Then what we do is this RV and Fagaras will put into the frontier list. So this RV will put and Fagaras will put. Now, how we'll explore next? We'll explore next with the help of again the depth. So in the depth of RV, what we have? We have Pitestia. Pitesti. Pitesti is one city here. So RV has been explored. Pitesti. Pitesti is a goal node. No, it is not a goal node. Then we'll put it here. Then Fagaras. Fagaras will be explored because we'll explore one level at a time. Bucharest. We got Bucharest. Bucharest is compared with the goal. Yes, it is a goal node. So here only we'll say that I find the goal node. And I find the goal node. I'll go from S to, Subui to Fagaras. And from the Fagaras, I'll go to the Bucharest. Now, what is the total cost? What is the path cost? So I'll calculate the path cost. From here to here, it is 99 plus here to here, it is 211. So how much it is? It will be 310. 310 is my path cost using the breadth first search algorithm. Now, second, we'll apply the uniform cost search algorithm. So in the uniform cost search algorithm, also we have the two data structure. One is called frontier. So is my frontier list. Then I have explore list. Now in a uniform cost search, what will happen? The initial node, this has taken as into the frontier. And this initial node will be first taken to remove, will be popped. Once it will be popped, then it will be compared with goal node. S will be compared with goal node after the popping from here, frontier node. So it is a Bucharest. No, it is not a Bucharest. Then S will be explored. So child of S will be explored. What is the child of S? Is Rumiki Vikala. So RV. And then Fagaras. What is the cost? Is 80. What is the cost? Is 99. Now, what is the path cost? So we'll calculate the path cost here. The path cost is 80. What is the path cost here? Is 99. Now, according to the path cost, we'll put that node into the frontier node. So who is in the least cost is RV, then Figueres. Now, next node has to be explored is RV. Now, RV will be removed from frontier list and compare with the goal is Bucharest is not the Bucharest, then RV will be explored. So the RV will have only one, which is Pitești with cost of 97. Now, what is the path cost? The path cost here, it will be how much? 177, right? And it is the new child, which is not there here. And what is the cost here is F will have 99 cost and P will have 177. So I can put P here, which is Pitești. Now, which one has to be explored? Definitely least cost has to be explored. This Figueres has to be explored. So Figueres, is it equal to Bucharest? No, it is not equal to Bucharest. Then Figueres has to be explored and we'll find out the Bucharest. What is the cost here is 211 is the cost. And what is the total cost of reaching the Bucharest here is 99 plus 2 is 310. So right now what we have in my frontier node, because right now I have the Bucharest, which is in the child node. Sorry, RV has explored, right? F Figueres has already been explored. Now, what is my child? Child is Bucharest. Bucharest is not there. P has this Pitești has 177 as the cost. Bucharest has 310 as the cost. So I'll put Bucharest after that. Okay. And Bucharest has cost 310. Now next is the Pitești. So Pitești will be compared with the goal node. No, it is not a goal node. Then Pitești will be explored. Put it in the explore list and will be explored. So I'll got Bucharest here. And what is the cost from here to here is 101. And what is the total cost here? What is the total cost? It will be 287 is the cost. Now we find a new child. This child which already been here has the cost 310. So this child will be replaced with this child, okay, with the cost of 287. Now the next is B. B will be removed from the frontier list, and this Bucharest will be compared with the Bucharest. Do we reach the goal? Yes, we reach the goal. And what is this path? This is the path. So this is my goal. Not this. This is not the goal. This is the goal. Okay. And what is the path cost? So the path cost here that we find here is, which has already been written, is 287. So to reach the Bucharest, here the uniform cost search will give you the path cost as 287. But the breadth first search will giving you the path cost as 310. So you can see the comparison between the the breadth first search and uniform cost search. Who is giving you the least cost? Definitely the uniform cost search will give you the least cost than other searching algorithm. So as we have compared these two searching algorithm here with one problem, so you can see the difference between two searching algorithm, and this is how we can do the or we can perform the searching. Definitely the BFS will give you the solution quickly, but the thing is that whether the quick solution is the optimal solution or not. because it is not an optimal solution and we are looking for the optimal solution. So this is the uniform cost search, which will give you the optimal solution. We are going to solve 2 more questions related to uniform cost search, and we'll see how the Dijkstra is the basic of the uniform cost search. Okay, so that we'll see into the next